Well, hello and welcome back to our journey with acid and base chemistry. So far, hopefully we have looked at the concepts of acids and bases according to Bronsted-Lowry theory. We're more comfortable now with choosing the differences between strong and weak acids and bases and how we might define this. Also, we've looked at reactions of acids and how we would write equations for these. Now we're going to start bringing it back to the pH scale, which is probably what you first learnt about in terms of acids and bases. And then we're going to start looking at the mathematics of how we determine pH by combining this with our knowledge of concentration and what we've come to learn about the concentration of hydronium ions. So let's get started. The pH scale is basically a scale that has been put into place that allows us to describe the acidic or basic nature of a solution. Technically, the pH of any solution is going to be dependent on the concentration of H3O+, or interchangeably what we use the term H+ for. Okay, so in these cases, in all situations, the concentration of H+ or H3O+ is actually what we are being told about when we're being told about the pH. The concentration of H+ varies widely. Okay, so in battery acid, which is sulfuric acid, H2SO4 is actually in our car batteries. They're known as lead acid batteries. This is 10 to the 0.9 mole per decimeter cubed, or in VCE language, moles per litre. In pure water, we actually have 10 to the -7 moles per litre. Okay, so we're talking about here 1 times 10 to the -7 moles per litre. So this is actually a very, very dilute solution, and if you think about this, if this is pure water, this is going to be the concentration in what we equate to be pH 7. Okay, then in oven cleaner, we're talking about 1 times 10 to the -13.5, so we've reduced the concentration of H+ even further, taking us into what would be a base, because this is our oven cleaner down here. So in this region here, we're talking about 1 times 10 to the -13.5 moles per litre of H+, whereas in our strong acid that we're seeing in terms of our battery acid, we're actually up here, we're off in this very low region here with 1 times 10 to the 0.9 moles per litre. And of course, pure water at 25 degrees C, 1 times 10 to the -7 moles per litre for the concentration of H+ or H3O+ at pH 7. Essentially, what we're talking about when we're talking about acids and bases is the relative concentration to H+ and OH-. Previously, we have always said that a pH of 7 is equal to a neutral solution, and we're going to expand on this idea and say that a neutral solution is actually when the concentration of H3O+ and OH- is actually equal. And as we will come to learn, this occurs at pH 7 at 25 degrees C, but this pH value will actually change with changing temperature. So the better definition for us for a neutral solution is one where the concentration of H+ and the concentration of OH- is equal. If we increase the concentration of H+, okay, then making it heavier on this side, so we have more H+, then our pH decreases. Okay, just like on a seesaw, if you add more mass to one side, it goes down. So if we add more H+, our pH decreases, and our litmus will turn red, indicating that it is an acid. If we have more OH-, i.e. the greater mass is on the OH- side, so we have more OH-, the pH will go up. Okay, the pH increases, okay, indicating that it is a base, and litmus will turn blue. And these are our better definitions, okay? So a neutral solution is one where H3O plus is equal to OH minus. If we decrease the H3O plus concentration, we get an increase in pH. If we increase the H3O plus concentration, we get a decrease in pH. So this is more acidic. Okay, and this is less acidic or more basic. Okay. The other thing to note here is that each step on the pH scale relates to a times 10 difference in H3O+. So if we have pH 1, it will have 10 times more H3O+ than something at pH 2. To go from pH 2 to pH 1, I have to increase the concentration of H plus 10 times. This is because pH is actually a logarithmic scale. So the pH scale corresponds to the concentration of hydronium ions in solution, and is given, the pH value is given by this equation here. You'll notice it is the negative log to base 10, so you'll be using the button on your calculator that says log, which is our base 10 log, and these square brackets here indicate molar concentration. So when we type this into our calculator, we would put negative log to base 10, it'll open up the brackets, we type in the concentration of hydronium, close the bracket and hit enter, and the answer that we get will be our pH. So if we're good at rearranging logs, okay, then this means that if we rearrange this log, we will get that the concentration of hydronium ions is equal to 1 times 10 to the negative pH. Okay, so if you think back to the fact that we said that a pH 7 solution had a 1 times 10 to the negative 7 concentration of H3O+, this exponent here is equal to our pH. Okay, so if I said I had a 10-fold difference in concentration of pH, i.e. I timesed this by 10, my exponent would go up by 1, and I would end up with 1 times 10 to the negative 6, which would change my pH to 6. Okay, so each factor of 10 will change my pH by 1. If I decreased the concentration of H3O+ by a factor of 10, I would end up with 1 times 10 to the negative 8, and this would give me a pH of 8 because I've decreased the concentration of hydronium. Note, each time we are only talking about the concentration of hydronium. We're not focusing on the concentration of hydroxide here, we are focusing on the concentration of hydronium. In fact, pH means to take the negative log to base 10 of what follows that little p, which of course is going to be the hydrogen concentration in this case. So in pure water, the hydronium concentration is 1 times 10 to the negative 7 molar, so the pH of the solution is 7. The pH scale ranges from 0 to 14, okay, where 7 is considered neutral. Below 7 is acidic, and above 7 is basic. This is a very simplified definition of acid and bases, and you need to remember that this can change with temperature. The further away from 7 we are on the pH scale, the more acidic or basic the solution will be. So if we have a pH of 1, it will have a concentration of 1 times 10 to the negative 1 moles per litre. Okay, or 0.1 moles per decimeter cubed, okay, which is the same as moles per litre. So if it has a pH 2, then we change that by 10-fold. Okay, so this is an easy way for us to figure out the concentrations of hydronium when looking at pH. Okay, so we can look at this tabulated from 0 through to 14. We can see that the concentration of hydronium gets smaller as we go down. So this is a very, very low concentration of hydronium in a basic solution. Okay, so if the pH of a solution is given a value X, then we can find the concentration by saying 10 to the negative X moles per liter. Okay, so this is remembering we have a new formula now that the concentration of hydronium ions is equal to 1 times 10 to the negative pH, and that concentration will be in moles per liter. Make sure you make note of this formula. We will be doing practice with this later on. So if we graph the pH scale using ion concentration across our y-axis, pH across our x-axis, what we will see is that with high concentrations of H3O plus ions, okay, we have a low pH. As we increase the pH, we decrease the concentration of hydronium. And then if we plot this for OH minus as well, we will see that at this point, when the concentration of ions is the same, this is actually going to be our pH 7, or our neutral solution, where the concentration of OH minus is equal to the concentration of H3O plus. Okay, so that is it for our pH scale and noting how that equates to the concentrations of hydronium. In our next video, we will look at the way we can use these in calculations, and it will mostly just be practice calculations in the next video, and I'll see you there.